finally, we've gotten to dilations. Now, when we're talking about transformations, we have rotations, translations, reflections. These preserve congruence. These are isometries. A dilation is not. It is not an isometry. It does not preserve congruence. But what it does do is it does create a similar figure. A dilation preserves the same shape, but it's a different size. Okay, we're changing the size of our figure. We also may change the position. So, a dilation that results in an image smaller than its pre-image. If it gets smaller, it is a reduction or a contraction. If it gets larger as we go from the pre-image to the image, it's an enlargement or an expansion. And if it's going to get larger or smaller, all depends on its scale factor. If the scale factor is less than 1, it is going to shrink, it's going to compress, it's going to reduce. If it's less than 1. If the scale factor is greater than 1, it's going to get larger. It's going to be an enlargement, it's going to be an expansion, it's going to get bigger if that scale factor is larger than 1. If the scale factor is 1, there's actually no change at all. The center of a dilation is pretty important. We're going to see that in some examples here. All right. It says find the image of AB after a dilation with a scale factor of 2 in the center C. Okay. Well, first of all, if the scale factor is 2 and our segment is with a length of 4, well, we think that new segment length is going to be, it's going to be 8. All right. Well, we know the size of it, but what does it look like? What is its orientation? Where is it at? All those things. Well, I've got a ruler here. This will actually be pretty helpful for us. Meteor stick, and it's not a ruler, but we're using it like one. Now, how we actually perform this, we would want to measure the distance from A to C. So, a scale factor is 2. I measure the distance from A to C. I can see that distance from A to C is about 12 centimeters. So now I want to go 12 times 2 means I want to go 24 centimeters away from C to get my new point A prime. I find the distance from B to C. I notice the distance from B to C is about 11 centimeters, and so I'm going to multiply that distance by 2, and so I need to go 22 centimeters away from C to get B prime, along that same line that contains C and B already. I measured the distance. I doubled that distance in this case because the scale factor is 2. So here's my dilated figure. It should have a length of 8, and the points should be twice as far away as they were before. Okay. All right. Did it. We got it. All right. Now, here it says apply a dilation to triangle JKL using a scale factor of 1/2 and center C. Helpful if I make these some nice points here. Well, I'm going to find the distance between J and C. Between J and C is about 8 inches. So I take that 8 inches, I multiply it times 1/2, which gives me 4 inches. And so I'm going to go 4 inches from C, which gives me my new point for J. I do need to make sure it's in line. That is my new point J prime. It should be half the distance between C and J. Very similar for L. I'm going to measure the distance between L and C, which is about 10. Cut that in half. 5 units from C is my new L, And finally, from C to K, I stay in inches. It's about 7.5. Half of 7.5 is 3.75. If I go 3.75 away, I get my K prime. When I connect these, notice when the scale factor was less than 1, it got closer to the center of dilation, but also every part of my figure was compressed. It was shrunk. It was reduced by a half. The distance between L and J is now half that distance, and that is the same for all the sides because we've created a similar figure. Now when we're dealing with a coordinate plane and our dilation centered at the origin, this becomes very, very simple. Triangle DEF has vertices D at 4, 6, E at 6, 2. Sorry, didn't need that apostrophe there, and F at 2, 4. Okay, so there's our original shape. It says, graph the image after a dilation centered at the origin with a scale factor of 1/2. Well, we know it's going to get closer to our origin. We know all these distances are going to shrink. They're going to compress. The distance between D and E is going to become half of what it currently is. But because it's centered at the origin, this only works when it's centered at the origin. Listen to me. Only works when it's centered at the origin. We can multiply all of our coordinates by the scale factor. D, which was 4, 6, is now 2, 3. There's D prime. E, 6, 2 is now 3, 1. There's E prime. And F, which was 2, 4, is now 1, 2. There's our F prime. So as they get closer to the origin, it's the same orientation, it's the same shape, but it is a different size. Finally, it says a student wants to scan and enlarge a piece of art that is 6 inches by 8 inches. If the student selects the 150% enlargement function, what will the lengths of the sides of the copy be? How does the perimeter of the original art compare to the perimeter of the copy? Here's our original 6 by 8 piece of art. We want to enlarge it by 150%. We are creating a similar figure here. 150%, we think of that as 1.5. 6 times 1.5 gives us 9. 8 times 1.5 gives us 12. So the perimeter of the original piece of art, 14 plus 14, the perimeter is 28. We're in inches. Here, 9 plus 12 is 21 plus 21. The perimeter is 42 inches. Notice that as the side lengths were multiplied by 1.5, the perimeter was also multiplied by 1.5. These are similar figures, and we know that with similar figures, we can see the ratio of the sides, but the perimeter is going to have that same ratio.